Good morning.
Good morning, Professor.
Hi, Justin. How are you?
I'm doing well.
Yeah, just we'll wait for just a couple of minutes and get started. Hi, Anthony. Are you online?
Yeah. How are you doing?
Oh, pretty good. How are you?
Okay. Awesome. Yeah. Very good.
Okay. Well, as you guys noticed that we are now at the end of the third week, and in the first 2 weeks we learned about material selection, basic properties of materials, and started reviewing how to calculate stresses. So by the end of this week, we will have most of the information needed to calculate stresses for any component. And then next week, we will continue on the same course, just finalizing stress calculations. And that will be part of the infrastructure that we're building for the design. And then half of next week and the following week, we will be dealing with the issue of deflection, because we have two issues to deal with, stress and deflection in the design. So the deflection is going to go on half of week 4 and all of week 5. And I think that would be kind of take us to about the middle of the class, midpoint, and then the remaining part of the class is going to be more on applications to design. So this is just kind of a little bit orientation here. Okay, so what I wanted to do is make just some comments on a few areas that I feel are important for solving the homework problems. I'm not going to specifically just work on homework problems, but I will point to what needs to be done in dealing with a few issues in stress calculations. So if you look here on the screen, first is when we have stresses due to bending, and if we have bending on two axes, so we have a bending moment on the y-axis and a bending on the z-axis, then what we do, we combine them together to produce, because each one of them will give us an axial stress. So the two axial stresses can be combined together or can be added together in one line. So if you look at this line here, the axial stress is the sum of the two stresses, but we have to note that due to the rotation convention of the two moments, then the stress due to the mz moment is minus mzy over iz, and then the stress due to the y moment is plus myz times z over iz. So that's kind of the convention for the two sources of the same axial stress when we add it together. If it happens to be that we have a circular cross-section, as in most shaft designs, the situation is a little bit simpler, because the moment we look at it as a vector. So we add two vectors together, and we use Pythagorean theorem to find the resultant vector of the two moments. So it becomes easier. So if you have here, this m is the resultant. And the resultant is, using Pythagorean theorem, is the square root of the sum of the squares. So it becomes quite straightforward, and we just use the formula 328. So this kind of general comments on bending stresses, and I have this quick example that shows you that we have a beam, and the beam has two types of loading. One vertical and uniform, in the negative y direction. So we have minus 50 pound-foot per inch. So it's per inch, which means that it's kind of a force density. It's not really a total force. So in order for us to find the total force, we have to integrate that load. And then we have a concentrated force of 100 pound force at the tip C. So that's these are the two sources that we need to deal with. I wanted to make sure that we have the recording. Okay. So these are the two sources that we deal with, and that can produce two types of moments. One due to a uniform loading in the negative y direction, and one due to a concentrated load. And we have to make two different moment diagrams, and the moment diagrams that we have are here. So due to the uniform loading, the moment diagram, if you integrate twice, you get a parabola. So a uniform load, first integration give you a linear, second integration give you a parabola, and the maximum is 1/2 times the length times the intensity square. So this is the 1/2 times the intensity of the load times the length square. And so it gives us a maximum of minus 1600 on one end. And then the concentrated load that is applied at the tip C gives us a moment maximum of 800 on that end. But the moments are actually in two different directions. One is M along the Z direction, and one is M along the Y direction. So when we consider those in a combined way, we have to, if we have a rectangular cross-section, it would have two different moments of inertia, but here is a square cross-section, and the moment of inertia is BH cubed over 12. So in this case, BH cubed over 12 gives us the same moment for IZ and for IY. Same moment of area, or the second moment of area. So the axial stress is negative, and then this is my times, let me see here, as we go back, mz times y over iz. So mz times y, the maximum, the point A has location or coordinates y is equal to 0.75, and z is equal to 0.375 half. So we would just use this addition. We have the main point that I wanted to mention here is that we would have to have a net minus here and a plus here to give us the total. And then we would have a compression, tensile stress at point A and compressive stress at point B. So that's kind of the first comment that I have here on this type of calculation. The second comment is that in beam bending, in general, there is another kind of stress, which is a shear stress due to the vertical shear force. And the shear stress, as we analyzed in the lectures, is VQ over IB. So if you just go through the lectures, at the end of the day, you get a shear stress VQ over IB. So what am I trying to say here is how do we interpret this equation? How do you use it? In what condition? Under what conditions? First, we always look for the maximum shear. So the maximum shear is going to be when the V is maximum. So we have to be cognizant on how to compute the vertical shear at every point on the beam, the shear force diagram, and then the maximum Q, and that is really the key in these calculations. What is Q and how to find it? And the minimum B. So the minimum B is the width at any location. So let's see how this applies. So this applies, let's say, if we have an example here, and I have a beam, and the beam has a concentrated force of 488, and then we find the reactions by simple statics at the two ends. Then from that, we're able to find the shear force diagram, as you can see here. So the shear force diagram, we have a reaction, 366 gives us this force up 366, constant here, and then the 488 drops down to 488, constant, and then up minus 122. So this is what we've learned before, and we also can find the bending moment diagram by just area under the curve. Here would give us the height in this location, which is 1098. So we did the statics, and now we're ready to find the stresses. So in these kinds of calculations, we want to find the bending stress, and we want to find the shear stress, and we want to analyze failure. So to analyze failure, we will start using failure theory, which means that we want to find the maximum principal stress or the maximum shear stress. So that's kind of the point of all of these discussions here. So to get to that, we have to find the second moment of area, and the second moment of area of the I-beam is, we can do it two ways. One way is to use parallel axis theorem, and another way is to just do it simply by taking the second moment of area of a rectangle, like this rectangle here, and then subtract the second moment of area of this rectangle here, and then subtract the second moment of area of this rectangle there, which are the same equivalent. So it means that this would be much easier, because I can use b cubed over 12 for the big rectangle, the red one, and then I subtract two green rectangles, one here and one there, and that would give me the total second moment of area. And that's what we're going to use. I think we did, for the T section, we did use the parallel axis theorem to do each part on about its own centroid, and then transfer the second moment area to a common centroid by adding the area times the distance squared. But here we're just going to do the subtraction idea. So the subtraction idea will give us the, see, this is not responding here. Okay, here we go. So the subtraction idea gives us the second moment of area, and the second moment of area is BH cubed over 12 for the big rectangle, minus twice of the second moment area of the two smaller rectangles. So we prepared now the foundations to do both the bending, the axial stress calculation, and also the shear stress. So let's see how this happens. Okay. All right, so the bending stress, the axial bending stress is easy, because it's M times C over I. So we found I, and then C is the distance to the top or to the bottom. But what we're interested in now is the shear. So the shear is VQ over IB. So let's look at Q as the critical element of that. Q is the moment of area about the common centroid, or the neutral axis. So if you look at the neutral axis right here, and I'm trying to find the moment of area about that neutral axis. So let's say I have a little area here, then all I have to do is find the center of this area, find the area, and then find the distance of this center from here, and then Q for that area will be equal to the area that I have times the distance d. So very simple. And if I have many areas, I can just apply that successively. So the key is to find this distance d. So if I just have here, you can see now I have, in this calculation, I have QA is the Q for the point A, which is here, and the Q at, it's Q at point A. It means that everything above point A. So everything above point A will be this piece. Let me try to expand it a little bit. So I want to have Q of this section by finding the centroid and on the distance and times the area. And then I want to find also the moment of this section, which is the area of this section times its own distance. So I have a D1 here and a D2 here. And then I just add up. So that's kind of the idea that I have here. And when I do that, you find that, let me see here, you find that QA is area 1, which is this here, 2.33 times this height here, 0.26. So this is area 1 times the distance. And the distance is 2 parts, the 1.24 from here to here, and then half of the width of the flange. So it's 0.26 over 2. So that gives me the Q as a result of the first section on the top. And then the second section is the skinny one here, this one here. So it is, I find its area, 1.24 times 1.7, and then I multiply by the distance off of the neutral axis, and I add. So if I do that for all of the points, so for point A would obviously have the highest Q, point B would be the same as point C, these two are the same, and they have the Q is just only the first part here because we're looking for the effect of the area above that point. And then the interesting part is that at point D, Q is equal to 0 because there's nothing on top. There's no area on top. So the area is 0 basically on top of that point. So that kind of gives me all of the ingredients that I can use to put in the calculation for VQ over IB. It is important also to note that the B is local. So the B is the width. For example, if I'm looking here, the B is very large. If I'm looking here, then the B is small. So what happens is that the shear stress in the flange is very small, and then it have a jump at the interface, and then becomes large as I move towards the center. So it looks like a kind of a hat, but basically it's a part of a parabola, and the parabola here, this is the distribution function as a result of adding the section. So as we move towards the center, we're adding more and more Q, accumulating it to give us higher and higher shear stress. So the moral of the story is that the bending stress would be the largest on the top or the bottom. That's an axial direction, while the shear stress will be the highest at the center. So for beam design, we don't know where would be the failure point. It could be a result of the axial stress at the top or bottom, or it could be a result of the shear stress in the flange section. For example, if we're in the web section. So if we make the web very thin, then we could have failure due to shear. If we make the flange too far from the center of the beam, then we can have failure due to tensile stresses. And to make that judgment, we have to add up the two stresses using Moore's circle to find the maximum principal stress, and then use this as a criterion for failure. So that's kind of what's next here, is the idea of combining. And the idea of combining is when we combine, I want to find the tau max. And the tau max is, in this case, I have only sigma x, only sigma, there's no sigma y. So it'll be sigma x over 2 squared plus tau squared. So the tau max formula from Moore's circle, it becomes simple, and it's sigma over 2 squared plus tau squared. And then I can apply it to point A, B, C, D to find where the maximum shear would be. Okay, I can stop here just to see if there are any questions. Okay, any comments?
None here.
Okay, so moving on. One other area that I wanted to make some comments on is the area of shaft design as we move on, because that would be, we would just kind of build on the different considerations. And the shaft design, there's a couple of problems related to the homework assignment. One of them is, how do we connect torque to power, to forces, to moments, and so forth? And that is illustrated in this example, partially in this example. The homework problems will build on that. So here, if you have a shaft rotating at constant RPM, means constant speed, it's not accelerating, then the net torque on that shaft should be 0, right? So what happens is that you have, in this case, you can have transmission from one axis to another axis, let's say 90 degrees axis transmission, as in this example. Or you can transmit the power in the same direction. So these are possibilities. So in this possibility, I have a torque that is caused by pulleys, and the pulleys have tension on the two sides. One side has to carry higher force than the other side. Otherwise, the pulley is not going to spin. So usually the tight side is much higher tension than the loose side. In some cases, as in one of the homework assignments, the loose side is given as a fraction of the tight side. We can say the loose side is, let's say, 15% of the tight side, or 10%, or any number, or any percentage. Or they can give us both the tight side tension and the loose side tension, as you can see here. So the tight side is 500 and loose side is 100, and we have the dimension of the pulley C. The diameter is 8 inches. Then we can calculate the torque as the difference between the torque caused by the 500 minus the torque caused by 100, and the torques, we just compute them at the center point. So it'll be 500 times 4 minus 100 times 4. And that has to balance exactly the torque on the smaller pulley, which is half of the diameter of the larger one. And it has, again, a tight side 1000 and a loose side 200. If the loose side is not given to us, we can obviously compute it because the torques have to be equal. So this is not necessary to be given, or vice versa. Or they can give you a relationship between these two. So you can play a few games here to utilize the fact that the torque is equal to, net torque is equal to 0. Okay, having done that, then the consideration is, what is the distribution of the moment and the force on the shaft? Okay, so this is kind of what we have here. I think we discussed this a little bit last time, but the what we have here is that the tensions combine in one direction, so it'd be 600 together, because the two tensions are pulling in the same direction, so it would be a concentrated force of 600, and the two tensions here combine together in 1200. So you notice that the concentrated forces are acting one in the negative y direction and one in the positive z direction. So we set that aside, and then we look at what other, these two concentrated loads, the end result is that they're going to do reactions at the end. So we can determine that from statics, and they're going to give us moment distribution that is linear, but on two different planes. So if you look here, you will have, this is the linear distribution on the of the moment on the z, m sub z, and this is on the xy plane, and then you have m sub y on the xz plane. And we discussed last time that maximization of the moment can occur at different points. So we choose critical point B and C. We have the choice here, and we look for the 4 different values of the moments, and then we find the axial stress as a result of the combined moment with the formula that we discussed before. So this is one type of loading. Then we go back and see what else do we have in shaft problems. We would have now to consider a concentrated torque of 1600 acting at C, and a counter torque of 1600 acting at B. So if you look at the torque diagram here, you get 0, and then jump up to 1600 constant, and then down 1600 constant, 0. So the torque here between these 2 points, B and C, is 1600, and is 0 here and 0 here. And therefore, in a design, if I'm looking for shear failure, the shear failure is going to occur between points B and C. So the shear failure is going to occur somewhere in here. And if I'm looking for really a failure assessment, as we will see in maybe in a couple of weeks, then we will have to apply a failure theory by combining the shear and the principles, either principal stress or maximum shear, or some other combinations that we'll study. But that's kind of preparation for what follows. So in this case, if you look here, we have to compute, because it's a round cross-section shaft, it makes it easier, so we use vectors. And instead of doing it with the sum formula, that we have another way, is if there's a round cross-section, we just use the vectors, and we find the net or the resultant vector moment at B, and the resultant moment at C. And we find that at B it is larger than C. So we base our design on finding the bending stress at B, MC over I, and that gives us 24.89 KSI. Then, to complete this analysis, we look at the torsional shear stress, which is T times C over J. And this is the T is in between, 1600 is the T. And then we just work it out. We find 2.414. And then we can use these two values in a Moore circle, or we can use them in failure assessment as we wish in the future. So that's kind of what second one. Then one more idea here before I just look at questions is on torsion. We have a couple of problems on torsion in the homework assignment. So in torsion, we have two formulas. We have a formula for finding the shear stress. This is from, it's called Brett's formula. The shear stress in the thin wall. In the thin wall, what we do is we always consider the mean, the mean median line. So whatever the cross section is, we just go between the inner wall and the outer wall and put a median line in between, and then reduce the cross section into a simple line. So the cross section could be like this, or it could be like that, just a simple line. So this simple line has two properties. One is a length, which is the sum of this plus this plus this plus that. And the other one is the area. So the area. So we have to, whatever cross section we have, we immediately calculate the perimeter length and the enclosed area and prepare that for finding things. And the two things we find are the shear stress and the angle of twist. Shear stress is the torque applied over 2 times the area, main area times the thickness. And the angular twist, which is the torque times the length over 4g times the area squared times t. Now, what's important to note is that the angle of twist is per unit length. So if I have the longer the shaft, the more twist is going to have. So I have to calculate theta 1, and in order for me to calculate theta, so this is important, theta would be equal to theta 1 times the length, however long the shaft is, to give us an angle of twist. And in design, there are limits to how much we can twist the shaft, so it becomes important to reduce theta 1 as much as possible by making G very high, or by using thicker cross-section and so forth. So these are the two formulas we used, and here's an example. You have a square cross-section or rectangular cross-section, 2.5 by 3.6. The wall thickness is 1/8, and then we have a maximum allowable shear of 11.5 KSI. So maximum allowable shear, it means that this is given. Once this is given, then I can determine the maximum allowable torque. If I have the dimensions, I can determine the corresponding torque. Once the corresponding torque is given, then I can determine theta 1. So just knowing the allowable shear stress can tell me what is the maximum torque, and the maximum torque can tell me how much twist this cross-section is going to have. So that's what we did here. First is geometry, the area and the perimeter. Second is from knowing tau, then I can find t. Third, from knowing now t, then I can find theta 1, and knowing the length, then I can find theta. And it's very important that theta is in radians, always in radians. So I convert it to degrees. So I think that's it for the comments, general comments. There's one on the power. Let me see here. No, a couple more. Okay. There's one more comment. There's a couple of problems in homework assignment related to pressurized cylinders. So in a pressurized cylinder, we can have internal pressure and external pressure. In principle, or sometimes, or most of the time, the external pressure is zero. But if we have an external pressure, then we get two types of stresses. One is in the hoop. Okay. Maybe I can illustrate that a little bit better here. So if I have the wall of a cylinder, then the wall of the cylinder will have a stress in the hoop direction. This is a hoop direction. We call it sigma tangential. And a stress in the axial direction, we call it sigma longitudinal, L. And the stress in the radial direction, we call it sigma sub R. So these are three types of stresses. And what is the story about the pressure vessel? Story is that we want, given pressure or dimensions or combinations, find these three components of the stress and determine failure. So determine failure, meaning find the maximum shear stress or find the maximum principal stress. So here we have the tangential stress equation, the radial stress equation, and we can find the longitudinal stress knowing the axial condition, constraint on the axial condition. So if we want to find the shear stress, let me see. So the shear stress, for example, in this case, I have the tangential stress is, if I have internal pressure alone, is given in 350, and the radial stress is given, and the shear stress is equal to 1/2 of the largest stress minus the sigma smallest. This is the application of Mohr circle in 3D, or stress transformations in 3D. Tau max is the radius of the circle. The radius is half of the diameter, and the diameter is the difference between two stresses. One is the highest, one is the lowest. It turned out to be in the pressurized cylinders that the highest is the tangential and the lowest is the radial. So if I take the difference between these two and divide by 2, that would give me the maximum shear, and therefore I can use that to determine the possibility of failure of a pressure vessel due to shear stress. So these are basically here for, there are other types of stresses. I think we will deal with that next time. But I was trying to find the idea of torque, yeah, here. So the last element of this section for today is that when we use a shaft, we don't apply a torque. Usually we apply some kind of horsepower, so the engine delivering horsepower. So if we know that the horsepower is equal to the torque times the angular speed, this is kind of basic physics, horsepower is equal to the torque times angular speed, similar to saying that the work done is equal to the force times the velocity. So it's the same idea. Here, the horsepower is like power, and then the torque and the angular velocity are given in the basic units. So if we're using basic units, the power has to be in watts, torque in Newton meter, angular velocity is radian per second. But in practice, we don't use these units. We use either in US customary units, we use the horsepower is in horsepower, or the power is in horsepower. The torque is in pound-foot-inch, and the speed is in RPM. So in this case, the horsepower is equal to the torque in pound-inch times the RPM divided by 63,025. So that's the US customer units. If I want to apply the SI units, then the horsepower would be equal to the torque in watts times RPM n divided by 9.55. So this just comes from the conversion. Anyway, so if we're given now horsepower and RPM, we can obviously find the torque and then drive the shaft like in the previous examples that we talked about. Or if we want to deliver a particular torque and we have only a certain amount of horsepower, then we would be limited to a given RPM. So there are some considerations in the design that relate the transmission of power to the torque, and then the torque will go on to give us localized forces, as we've seen in the case of the pulleys, and then give rise to bending moments and also torsional shear stresses. So that's what I kind of have in terms of prepared presentation, and I would like to see if you guys have any questions. Justin, do you have any questions?
When determining the tau max with the pressure cylinders, will the longitudinal stress come into play very often?
Not in our considerations. That's a good question, because the longitudinal stress for a thin wall pressure vessel is usually half of the tangential, and the radial is usually very close to zero for a very thin tube. But if you have a thicker section, then it follows that the sequence of stresses would be the tangential is the highest, longitudinal is the middle, and the radial is the lowest.
Got it. Thank you.
Yeah. Kristen, do you have any questions?
No, I'm pretty good. Thanks.
Okay. Anthony?
Pretty good also. Thank you, though.
Okay. All right. I think that completes our office hour today, and we're going to have one. I'm going to be on travel to New Zealand next week, so I'm going to try to make it up the following week, maybe either Monday or Tuesday, and I'll send an email to everybody.
Sounds good.
Okay. All right. So have a good weekend, and we'll see you next time.
Same to you.
Okay. Thanks. Bye-bye.